Okay, we're gonna start right now, and I would like to say good morning to everyone here in the first session of the ECTI's Conference 2022. Okay, it is the first session of the electromagnetics and antenna sessions, and we have my name is Kirisak Pabua, come from Kimukut, University of Technology, North Bangkok. Okay, I am the chairman here. Okay, for today, I would like to talk about a little bit about the rule of the session. The whole session will be praised the videos, and the videos maybe 10 or 12 minutes, something like that. And we have the time for the discussion a little bit, 3 minutes. Okay, and today we have 5 paper. Okay, we're gonna start first. I would like to invite the first presenter, first videos. Okay, the title is the design and fabrication of the microstrip 4x4 Butler matrix operating at the 2.59 GHz for 5G applications. Okay, the host, please show the videos. Okay, thank you.
Good morning, everyone. My name is Atawutilakit. I am a presenter at the topic Design and Fabrication of a Microstrip 4x4 Butler matrix operation at 2.59 GHz for 5G application. The content of this topic is have 4 contents. First, introduction. Second, design and fabrication of a microstrip 4x4 Butler matrix network. Third, measurement results, and the last one, conclusion. The introduction. The sweep beam antenna is the one of the smart antenna type, and the antenna is need to adjust only the directional of the beam, and the sweep beam antenna need to have a beamforming feed network that can adjust the phase angle of the signal for each antenna element, and that's why the Butler matrix is important. The Butler matrix network is for sweep beam antenna with a number of input and output ports that depending on the number of antenna elements used. The resulting of the sweep beam antenna is have an orthogonal beam at different direction, and it have a small and is easy to build and have a low cost. The 4x4 Butler matrix network consists of 3 types of box. The first box is the 90-degree and TTB hybrid copper or the quadratic copper used for box. And the second is the crossover. Copper is just 1 box, and the last one is the 45-degree delay line phase shifter is just 2 box. I will describe about how the 4x4 Butler matrix is work for the antenna system. If we send the signal to input port 1, then they will give a 4 output signal is have a different phase shift from the input, and then the 4 different signal from the input will go to the antenna, and the phase antenna will give a beam direction to zeta 1. But if we send the input port 2, and if you give a 4 different phase shift of the 4 output port, and the directional of the beam antenna will change from the zeta 1 to zeta 2. That's why the 4x4 Butler matrix network can be changed from the zeta 1 to zeta 2 with the different phase shift from the 4 output ports. Design and fabrication of a microstrip 4x4 Butler matrix. The 4x4 Butler matrix network for design depends on the 2.59 GHz and low-cost FR4 substrate. The FR4 substrate is have a 4 characteristics. The first is the direct electric constant is 4/4.4, and the loss tension is 0.014, and the substrate thickness is 0.8 mm, and the copper thickness is 0.0039 mm. And figure T is show the low cost FR4 substrate board, and figure 4 is show the fabricated machine that used to fabricate the 4x4 Butler matrix network. This is called LPKF. And figure 5 is show the duplicate 4x4 arithmetic network with the low-cost FR4 substrate board at the 2.59 GHz. Design verification of 90-degree and 3 dB hybrid copper or quadrature copper. The characteristics of the hybrid copper: when the signal source is 0 dB, the output port will give a half power of the input port as -3 dB, and the output phase shift from the output port. When the output port is different from the input port, the phase shift from this is 0, but the other port, output port, is the phase shift difference with the input port is 90 degrees, and figure 7 is show the schematic of hybrid copper that's designed from the theory equation. The width of the microstrip line in each part depends on the characteristic impedance Z0, and the length of the microstrip line in each part depends on the different phase angle of the output port is 90 degrees. And the last figure is show the fabricated hybrid copper that use the optimized value to create it. Design and verification of the crossover cover. The characteristics of the crossover cover: when the input is 0 dB, the output should have the same power as the input port, that's 0 dB, and phase difference from the output port and input port is 0 too. That figure 10 is show the schematic of the crossover that's designed with the theory equation. And from the picture, the structure of the crossover is similar with the two hybrid copper were cascaded together, and some width and length of the crossover can be calculated. With the same hybrid copper, that's Z0 divided square root 2 and lambda divided 4, and Z0 and lambda divided 4 as same as the hybrid copper. But the middle part should be pre-calculated, the width and impedance of 2Z0 and input part and output part. It should recalculate length with lambda by 8. And figure 11 show the fabricated of the crossover with the optimized values. Design verification of the 45-degree phase shifter. The characteristic of 45-degree phase shifter: when the input port is 0 dB and 0 phase, the output port must have a 0 dB same as the input, but the phase should be different from the input is 45 degrees. And the 45-degree phase shifter is designed using the same microstrip line as the hybrid copper and the crossover, but the length of the 45-degree phase shifter is cannot assemble into the 4x4 parametric network because its 45 degree is designed with a lambda by 8 that can assemble in this circuit because it's too short. We will recalculate with the characteristic of phase in microstrip line that the 45-degree phase shift is mean a phase angle change of 315 degrees. So the new length is for 45 degree is 7 lambda divided 8, and figure 3 is show the schematic of the 45-degree phase shifter is new design with the theory equation. So, and figure is show the fabricate of 45 degrees phase shifter with the optimized value for have the similar 45 degrees and 0 dB. Measurement result of the 4x4 parametric network. The measurements were performed using a network analyzer, and the network analyzer can be analyzed as parameter. we will consider the three parameter is the phase shift of S21 and insertion loss is the magnitude of S21 and return loss magnitude of S11. And this figure is show the measurement of 4x4 parametric network. Measurement result of insertion loss S21. The magnitude of S21 is mean the insertion loss of S21. And I will example how to measure the 4x4 parametric network. So I will use the network analyzer port 1 connect to the input port and network analyzer port 2 connect as the output port 1 and another input port and output port will terminate by the meter 50 ohm and then I will send the power from the input 1 and make sure the power transfer to the output port 1 and I give this result in the table 4. So the left character is show the maximum magnitude and minimum magnitude of S21. Measurement result phase shift of S21. The table 5 is show the phase shift of the S21 with the input port 1, input port 2, input port 3, and input port 4. How to measurement it? I measurement with the network analyzer. Use the port 1 of the network analyzer connect to the input port 1 and port 2 of the network analyzer connect with the output port 1 and then I will send the signal 0 phase to the input port 1 and make sure the phase shift difference from the input port 1 and so I will got the phase shift of output port, phase shift difference from the output port and input port. And the left line, the left character is show the maximum error when compared with the ideal case. Conclusion: the prototype 4x4 parametric network has an average insertion loss is 7.92 dB and return loss is less than 15 dB, and the maximum phase angle error from the ideal case is 28.28 degrees. And this prototype can be integrated with a smart antenna system and can enabling for narrow beams and orthogonals in the direction to be aligned at different input ports. And this prototype is allowing for reduced signal interference and power transmission of the antenna system for the 5G application. Thank you for your attention.
Okay, thank you so much, Vicente. Okay, this time to discussion. Any questions, please? Okay. Okay, I have some questions for you for the first paper. Hello, presenter. Hello. Hello. Okay, I would like to ask some things about the why you use the hybrid couples instead of the power dividers, conventional power dividers. Can you answer me? Hello.
I use the hybrid couple because it's easy to design which the it's easy to design with the couple theory in a different.
Okay.
Yes.
You need some different phase or something like that.
Yes.
Right. Okay. 90 degree different phase. Okay.
Yes.
Because the power divider provide you 0 phase chips, but the hybrids maybe you got 90 degrees phase chips. Okay.
Yes.
The last questions. I thought that you have some high insertion loss compared to the measurement compared to the simulation one. Can you explain the reason why you get some loss from the fabrication of some things?
Okay, can I share my
The loss from fabrication.
loss from fabrication?
Yeah.
Because the loss is from the. Can I share my presentation?
Okay. You use the microwave PCB board or the cheaper?
Yes, I use a FR4 that.
Oh, okay. That is the source of the loss, I think.
Yes,
If you use the very expensive microwave print circuit, may be better.
yes,
thank you so much.
And the important thing I think is because 45 phase shifter.
Oh, okay. 45 phase shifters.
Yes,
You get some loss from that element, I think. Yeah.
Yes.
Okay, thank you so much. Any questions from the audience? Can you ask some question to the presenter, or you can suggest some things? Okay, the time is end. Oh, thank you so much for the first presenters, and I would like to move to the second one. The second one, the title is the design and parametric study of the suspended conformal patch antenna. Okay, the host, please play the videos.
Good morning, everyone. My name is Sawapha Milabiev. Today, I would like to present about design and parametric study of a suspended conformal patch antenna. Outline, introduction, antenna design and structure, single patch antenna, antenna array, and conclusion. Introduction. Antenna array. Antenna array is widely used in wireless communication system. This antenna is a combination of multi-elements or array, so it can enhance the gain and directivity. For example, you can see figure 2. This is a phase antenna array. The total field of array can calculate by the multiple of element factor and array factor. You can calculate following this equation. The element factor is the radiation pattern of each element, and the array factor you can calculate based on a geometry. And additionally, the antenna array can control the direction by feeding the phase to each element without control the direction. Figure 3.4 shows the block diagram of phase antenna array, and the figure 4 shows the antenna array when steering the direction. In general, about the linear planar antenna array, the main beam has a beam pointing error, and the gain will decrease when switched the direction near the horizontal direction. Because of each element has a narrow beamwidth. You can see a figure 5a. It shows the 2D plots of array antenna. When each element has a narrow beamwidth, you can see the right side when it switches the direction. Near the horizontal direction, you will see the gain will decrease and it has a beam pointing error. But the way to decrease the beam pointing error and remain the constant gain of the array, each element has a wider beamwidth. So you can see a figure 5b. It shows the 2D plots of array when each element has a wider beamwidth. You can see the right side. It shows the gain remain constant and the direction are at the proposed direction. The one type of patch antenna that has a wider beamwidth than conventional patch antenna, as named a conformal patch antenna. You can see a figure 7 show the conformal patch antenna that's conform on the curved surface. From the purpose of paper, we want to design a single element of antenna array to be achieve reduce the beam pointing error and remain the constant gain of phase antenna array. So the proposed antenna as named as suspended conformal patch antenna or SCPA that has a wide beamwidth and high gain. The next slide is antenna design and structure. The proposed antenna is suspended conformal patch antenna or SPCA. The patch structure is rectangular patch. The substrate material is flexible FR4. The suspended structure includes the air gap layer between substrate and ground plane to be enhanced gain and bandwidth. And the suspended structure and bending structure can enhance the gain and wider beamwidth. You can see a figure 8 show the structure of the proposed antenna. From antenna specification, we decide the antenna operate at 2.45 GHz, and the radius of the curve will vary from infinity 60, 45, and 30 mm. You can calculate the patch structure following reference 1. From the table 1 show the parameter of the antenna from theoretical and optimization. From the optimized value are slightly different from the theoretical value because we want to matching the impedance. Since the proposed antenna is suspended structure, so we have to design a support for air gap layer to separate substrate layer and ground plane. The support is made from 3D printing with PLA material. The 3D printing structure is placed around the antenna, which is designed to minimize the effect on antenna efficiency. You can see at figure 13 show the structure of antenna with the support in the simulator. This slide shows the antenna prototype after fabricated in a different radius of the curve. The suspended planar patch antenna or SPPA with the radius of infinity. The suspended conformal patch antenna or SCPA will vary the radius from 60, 45, and 30 mm. You can see the prototype following figure 14, and the rest structure is a 3D printing structure. This slide shows the simulation and measurement result of reflection coefficient of S11. From the simulation, the planar patch antenna provides a good impedance matching than the conformal patch antenna. The resonance frequency will decrease when decrease the radius of the curve. From the measurement result, the measurement results are good agreement with the simulation result, but the simulate are better than the measurement result because of the mismatching of the impedance. You can see the figure 15 show the simulation and measurement result. This slide shows the simulation and measurement result of the radiation pattern. From the simulation, the beamwidth of the planar patch antenna was narrower than the conformal patch antenna. In the H-plane, the beamwidth will increase when decrease the radius of the curve. In the E-plane, the beamwidth remains constant when vary the radius of the curve, and the gain will decrease when decrease the radius of the curve. And the measurement result have good agreement with the simulation result. You can see the result following table 2, and you can see 2D plots of the radiation pattern compare the simulation result and measurement result following the figure 17. This slide is antenna array. For the purpose of the paper, I forgot on to design a single element for phase antenna array to be achieve a constant gain and decrease a beam pointing error when it switch the direction in the prescribed direction. So the single element should be wide beamwidth. And now we got a wide beamwidth antenna as named a conformal antenna. The next slide, I will show the simulation of the planar antenna array with each element is a planar patch antenna and the conformal patch antenna. So we will simulate and compare on the beam direction and antenna gain. You can see a figure 20. I show the antenna model in the CLT simulator. A is a planar phase array when each element is a planar patch antenna, and B, C, D is a planar phase array when each element is a conformal patch antenna in the different the radius of curve. This slide shows the simulation of antenna gain. From the result following toward 3 is the maximum gain in the different direction when switched in the direction of 0, 15, 30, and 45 degrees. From the result, both of planar antenna array and conformal antenna array, the antenna gain decreased when the direction increased. And another value is delta G value, is a maximum gain difference of antenna gain between the beam direction of 0 degree and 45 degree. The delta G of conformal antenna array was clearly than the planar antenna array. You can see a figure 21. It shows the normalized gain at 0 degree of planar antenna array and conformal antenna array with radius of 30 mm in the different direction. You will see the delta G of conformal antenna array is 0.8 dB, but in the planar antenna array is 2.3 dB. So the conformal antenna array is appropriated from a constant gain of phase antenna array. This slide it shows the simulation result of beam direction. Following table 4 is the comparison result of planar antenna array and conformal antenna array when switched the direction of 0, 15, 30, and 45 degree at 2.45 GHz. From the result, the planar patch antenna array has a loss of beam pointing error because of each element has a narrow beam width, but the conformal patch antenna array are slightly better than in a beam pointing error, especially in a conformal antenna array with radius of 30 mm. Conclusion. From the purpose of paper, I designed the single elements of the antenna array as named as suspended conformal patch antenna or SCPA that operate at 2.45 GHz. The simulated and measurement results were demonstrated, and the measurement results are good argument in the simulation result. From the result, show that the antenna beam width increased with decreased the radius of the curve. From the suspended conformal patch antenna planar array with radius of 30 mm has a constant gain of 65% when compared with the suspended planar patch antenna planar array. And the proposed antenna is really useful to achieve a unidirectional pattern and wide beam width, and for a constant gain phase array antenna application. Thank you for attention.
Thank you so much, presenters. And this time to discussions. Any question, please ask the presenter right now. 1, 2, 3. Okay, I would like to start the first question. And I thought that from the results, you get very wide beams, radiation beams, compared to the conventional planar antenna, right? For the single element. And can you explain the reason why? I mean, that in terms of the radiation mechanism or something like that, why you get broader beams compared to the planar configuration.
Hello?
Hello, can you hear me?
Yes. Can you repeat that question again?
Okay. Please explain to me why you get the beams, radiation beams of the conformal antenna is broader than the conventional planar antenna. In terms of the radiation mechanism or something like that.
We just compare phase antenna array can switch the direction with the electrical mechanism. It has switched the direction faster faster than the mechanical mechanism. So that's why I choose to.
No. I mean, I asked some the reason why you get the beam width is larger than the conventional one.
I think.
Let's see the figure 6. Figure 6, you got the conformal antenna provide very big beam width compared to the Panam one.
Because from my calculation from the initial equation, the conformal antenna that has a wider beam width than the conventional patch.
Yeah.
When switch the right direction from the both side, it can decrease the beam pointing error and the gain will constant.
Okay, and I understand that, but don't worry about that. Okay. Okay, for the second one, you get final result. You get the constant gains versus the angle, right?
Yes.
Switch beam angle. Can you explain me why the conformal antenna solve the problem? The reason why the conformal antenna array solve these problems?
Because for I think each element of a conformal antenna has a wide beam width. That's why can be solve the problem.
Okay. I understand that. Thank you so much. Any questions or some discussions or suggestions for this work from the audience? No? Okay, the time is time's up right now, and thank you so much for the presenters and answers. And I would like to move to the next one, the third paper. The third paper is about the dual band sport rectangular shapes monopole antenna with 2 rectangular tuning stub on the pressure frame on the GSM and WLAN. Okay, the host please play the videos. Thank you so much.
Hello everyone, my name is Pisanu San. Today I will present to about dual band per rectangular sharp monopole antenna with 2 rectangular tuning stub on polyester film for GSM and WAN application, which assists Professor Dr. Amnoy Leongwali as a consultant, Department of Electronic and Telecommunication Engineering, Faculty of Engineering, Rajamangala University of Technology, Thanyaburi. Content 1. Introduction. 2. Antenna design. 3. Antenna measurement. And 4. Conclusion. Introduction. Wireless local area network has been used all over the world, bring a signal in the business or various government agencies, and the communication system is reduce the cost of traveling and reduce the time of communication, making it faster and more convenient. The machines are popular to communicate with computers, mobile phones, tablets, and iPads. But there are also devices that are important for communication. Antenna for transmitting wireless communication, therefore, the antenna structure is continually developed. Its structure provides a frequency response based on GSM, DCS, PCS, IMT 2000, and Wi-Fi. Wireless communication use an antenna to send electromagnetic field and wave propagation into all communication devices. The monopole antenna structure are well known for directional radiation, pattern easy tuning, lightweight, low cost, thin structure, and compact size. They have also been developed into a tie band for mobile phone systems such as talking and surfing the internet. Therefore, the researcher has interesting in developing the antenna to support dual band that applying monopole antenna structure with rectangular tuning stub used for model to extend to dual bandwidth. The simulation result use the CST program to determine the base parameter on polyester film for the prototype antenna structure. Antenna design. The first step is the antenna design from the basic rectangular monopole at center frequency 2.45 GHz on polyester film at feature 2 with the dielectric constant equal to T.2. The second step involves tuning the range on the radiation pad for support resonance frequency at 0.85 GHz as shown in figure 3. When L1 equal to 61.2 mm, the reflection coefficient are less than -10 dB for lower frequency bandwidth of 0.91 to 1.12 GHz and 2.09 to 3.31 GHz as shown in figure 4 at area A and B, respectively. As a result, the GSM system frequency bandwidth was not covered at lower frequency in cycle A. The third step are to add a rectangular matching stub on the left corner of the radiation pad antenna top side to expand the frequency bandwidth as shown in figure 5. When W2 equal to 30 mm, the reflection coefficient are under -10 dB with lower frequency bandwidth at 0.76 to 0.98 GHz and higher frequency bandwidth at 1.68 to 2.77 GHz as shown in figure 6. Considering the simulation result of surface current density distribution at 0.85 GHz as shown in figure 7, the radiator region that affects frequency response is placed on top of the radiator. The antenna structure for the area has been optimized in this step. Finally, the rectangular tuning stubs are at both sides of the polyester film substrate for frequency bandwidth expansion, as shown in figure A, which L3 equal to 61.2 mm. The reflection coefficient appears to be acceptable, as shown in figure 9. The reflection coefficient are less than -10 dB for a lower frequency bandwidth of 0.76 to 0.97 GHz and higher frequency bandwidth of 1.89 to 3.28 GHz. The figure 10 shows the prototype of the antenna structure and parameter of proposed antenna. The figure 11 shows simulation result of the reflection coefficient when compared with all tuning antenna. From the comparison graph for tuning show that the back graph antenna has the base reflection coefficient cover frequency bandwidth 0.76 to 0.97 GHz and 1.89 to 3.28 GHz. Figure 12A show the prototype antenna, and B show measurement for network analyzer. The figure 13 shows simulation and measurement result of the reflection coefficient parameter S11. From the graph, it can be seen that the antenna has two matching frequency band 0.76 to 1.02 GHz and 1.63 to 2.53 GHz. The figure 14 shows simulation and measurement result of VSWR. The table 1 shows simulation and measurement result of antenna maximum gain for each frequency. Figure 15 shows simulation and measurement E-band radiation pattern at frequency 0.85 GHz, 1.9 GHz, and 2.45 GHz. Figure 16 shows simulation and measurement H-band radiation pattern at frequency 0.85 GHz, 1.9 GHz, and 2.45 GHz. Conclusion: the frequency bandwidth of these antennas are 39.05% at frequency 0.68 to 1.01 GHz and 42.88% at frequency 1.74 to 2.69 GHz with gains of 2.136 dBi and 5.026 dBi. This antenna is supporting for GSM 0.9 GHz and WAN 2.4 to 2.48 GHz. Include frequency PCS 1.85 to 1.99 GHz and IMT 2000 1.922 to 2.17 GHz frequency. The advantage of these antennas are easy tuning, lightweight, and low price material. Thank you.
Thank you so much for the video of the presenters. And this time for the discussions and questions from the audience. Any question from the audience, please? 1, 2, 3. No question from the audience. I would like to ask some things. Hello?
Hello, can you hear me?
Yes. Okay, very good. And I would like to ask about a little bit about the effects of the stop tuning. You use the stop tuning to increase the bandwidth, right? You use the stop tuning to get the dual band operation. But I would like to ask about the effects of the stop tuning to the radiation patterns. Did you study about the effects of the stop to the radiation pattern or not? Can you hear me? Hello?
Hello, sorry.
Okay, can you hear me? Okay. Okay, for the short question, what is the effect of stop tuning on the radiation patterns?
The radiation pattern is low. It's not it's the share is it mean the no stop, right?
Yeah, correct.
Is at stop is at a both stop for support for the
operating frequency, right? You got
Right.
the dual
Yes.
band.
Yes.
Yeah.
Yes.
But the effect to the patterns, radiation patterns. Oh, can you answer me? No.
No.
Okay, don't worry about that. Don't worry about that. That is the next study. Okay, for you. You can vary the parameter of the stop, or you can compare, like a comparison between no stop and present stop or something like that. Okay, for the next time. For the next times.
Okay.
That is my suggestion. And for the next questions, I saw that from your results, simulation and measurement radiation patterns. And I saw that you got some error between the simulation and measurements. And can you explain to me why you get big error from the simulation and measurements? You see the figure 14 and 15 in your papers. Left hand side, that is simulation, and right hand side, that's measurement. You got very wide beam for the measurement.
It's the main beam of antenna is direct in the y direction. Is
the measurement error maybe come from, did you measure your antenna inside the anechoic chamber, right?
yes,
Anechoic
yes.
chamber. Oh, why you guess really different. Don't worry about that. For the next time, you have to compare the error between simulation and measurement. You can plot in the same graph, okay? You can plot in the same graph to see what happens, to see the difference between simulation and measurement, something like that. Okay, this is my suggestion. Okay. And any question from the audience, please, or suggestions about the measurement or some things? No. Okay, good. Okay, thank you so much for the presenters. Thank you so much. And the next one, I would like to move to the next paper. The next paper is about the metal surface-based circularly polarization dual port MIMO antenna for the C-band uplinks application. Okay, the host please show the videos.
Good morning, everyone. My name is Natapat Subiyathithikun. I am currently pursuing a PhD at the King Mongkut Institute of Technology, Lat Krabang. Today, I would like to talk about my research topic of the metal surface-based circularly polarized dual-port MIMO antenna for the C-band uplink applications. My topic consists of the 6 sections. The first one is the introduction and background. The rapid development of the wireless communications technology has triggered the need to expand system capacity and data rate. Accordingly, multiple input, multiple output technology can effectively improve the channel capacity of the system by utilizing multi-antenna technology at both the transmitting and receiving end with the limited power and bandwidth. Most of MIMO antennas transmit only in a single direction, called linearly polarization antenna, which is not immune to the propagation losses, interferences, and multiple path distortions. Therefore, circularly polarized antenna was required due to it can propagate in the two orthogonal directions with the same signal strength, which is for the various orientation of the transmitting and receiving antenna. The circularly polarization requires the identical magnitude and phase quadrature of the two component axes of the electric field. Circularly polarized can be characterized by axial ratio, which is the ratio between the major and minor axes of the electrical field. Especially the ideal secondary polari is axial ratio equal 1, which is certified axial ratio less than or equal to 3. The next one, the metasurface. The metasurface are thin artificial layers consisting of the periodic arrangement in the dielectrical medium. They can be designed to manipulate electromagnetic waves by using surface wave property. Moreover, the metasurface can be enhanced the impedance bandwidth gain and polarized conversion. The second section is literature reviews. In this paper 1, they utilize the metasurface surrounding the corner truncate patch on the same substrate layer of the 4-port MIMO antenna to improve the impedance bandwidth and axial ratio bandwidth. In this paper 2, they propose the 4x4 patch MIMO antenna stacked with the metasurface for linear to circular polarization and measure coupling reduced by using the slot and the shorting pin. The third section is objective. To design the MIMO antenna for C-band uplink applications, to achieve wideband circularly polarized by using metasurface structure, and to apply metasurface to enhance impedance bandwidth, axial ratio bandwidth, and gain while maintaining the low profile. The fourth section is simulation and antenna design. In subsection A, we propose the metasurface-based circularly polarized single-port antenna, which is consist of 4x4 rectangular shaped metasurface element on the upper substrate, and the lower substrate consisted of a microstrip profile and the ground plane. The microstrip profile was tilted of 33 degrees at the x-axis on the lower substrate layer. The evolution of the rectangular shaped metasurface element, including of these traits, which are comparing with the magnitude ratio and phase difference. It can be seen that in figure 3, the antenna 3 achieved approximately identical magnitude and 90-degree phase difference over the C-band uplink spectrum frequency. The simulated impedance bandwidth of the single-port antenna is 31.5%, and axial ratio bandwidth is 14%, with the maximum gain is 7.54 dBi at 5.4 GHz. In subsection B, we propose the metasurface-based secondary polarized dual-port MIMO antenna, which consists of two components of the single antenna with the same substrate. The result found that the S11 is 13.9%, and the isolation S21 is less than minus 20 dB. And next, figure 7, the axial ratio and maximum gain are 14% and 7.3 dBi at 5.1 GHz respectively. The figure 8 shows the ECC and DG of the proposed MIMO antenna. The ECC is the envelope correlation coefficient, which is the metric for indicating the relation between either antenna, which is much less than 0.5. It clearly seen that the ECC of the proposed MIMO antenna less than 0.002. So next, the diversity gain or DG achieved greater than 9.98 dB over the C-band uplink frequency. This slide shows the radiation pattern for XC plane and YC plane at the 5.3 GHz and 5.8 GHz. It can be seen that the proposed MIMO antenna has the right-hand circularly polarized characteristic. The fifth section is comparison between existing antenna and proposed antenna. It found that this work which had two number of ports and achieved the impedance bandwidth of 30.9. Actual ratio bandwidth is 40. Maximum gain is 7.3 dBi, and high isolate is less than 20 dB. And finally, section is the conclusion. The new research proposed the reticular shape metasurface-based circularly polarized dual-port MIMO antenna. The circularly polarized can be provided by the metasurface stack on the microstrip antenna. The proposed antenna achieved the simulated impedance bandwidth and axial ratio bandwidth of the 13.9% and 14% respectively, rendering the proposed antenna suitable for the C-band uplink applications. Thank you very much.
Thank you so much. And this time for question and answers, please. Audience, please help me to ask some things. No, 1, 2, 3. No question from the audience. Okay, I would like to ask some things. And can you hear me?
Yeah.
Okay. And you did some antenna for the MIMO system. Metasurface, you apply the metasurface, right, for the MIMO antenna. And my question is, what is the standard of the correlations, coefficients, how much the value, I mean the conventional standard, and also the standard of the S21 parameters, do you know, right? For example, S21 must be lower than minus 30 dB or something like that. Do you have the standard for that?
Actually, the challenge of the most researcher have to be the reduce the S21 or isolate port low possible.
Okay.
It's not have the standard, but it's lower than the S11.
Okay, maybe 20 lower than minus 20 dB is okay, right?
Yes.
For your applications.
Yes.
Okay, thank you so much. And for the next questions, I saw that you calculate the envelope correlation coefficients ECC by using the radiations parameters E1 and E2. Okay, the integrates over 4 pi, something like that. And I know that you can calculate by the S parameters. Did you compare between the S parameter ECC from the S parameters and ECC for the field, radiation fields? Did you compare it?
I haven't yet.
Okay.
Because of actually is we use the PVC in the lossless environment. The S parameter is doesn't work.
Okay.
Yeah. But
Okay.
we must to calculate by using the reaction instead.
Okay, I see. E1 and E2, that is the directivity or the absolute gain, absolute patterns. Directivity, right?
Yes.
No loss in the calculation, right? For the equation one.
Actually is the power
From the measurement, right?
Yes.
Okay. Thank you so much. And the last questions, I would like to ask a little bit in the deep details about the sequential polarized generation. And it is very difficult to explain, but I would like to know your opinions, right? Okay. The CP mechanism is come from what element? I mean, it's come from metasurface, right?
Yes.
Not feeding element. Okay.
Not slot antenna.
Okay. And can you explain me a little bit why you get the CP from your unit cell metasurface in the mechanisms? Yeah. Don't worry about that. Okay, it's so difficult to explain. Yeah.
Yeah. Normally the slot antenna they generated the linearly polarization to the metal surface or the upper substrate, and then the gap between the metal surface elements have to divide the electrical in y-axis to the 90-degree electric field, and they have the equal magnitude of the electric field. Is that why is the can be conversion linear to the secondary polarize?
Okay, I think I agree with you, but I don't know the correct answer. Okay, but I agree with you right now. Thank you so much for the presenter. And any questions from the audience? No. Okay, thank you so much, presenters. Thank you so much.
Thank you very much.
And I would like to move to the last one for these sessions. Okay, the last one, we're gonna go to the titles. Design of inter-wideband inverted U-shaped slot antenna with reflector for the GPR applications. The host, please open the video clips.
Good morning, all participants. My name is Thanakon Sutham. I come from Department of Electronic and Telecommunication Engineering, Rajamankara University of Technology, Thanyaburi. Today, I would like to present the research work in the topic of design of ultra-wideband inverted U-shaped slot antenna with reflector for GPR application. I have divided my presentation into 5 parts. Firstly, introduction. Secondary, objective of this research. Next, antenna design and result. Finally, its conclusion. I start with introduction. Ground penetrating radar (GPR) is one of the non-destructive methods of subsurface sensing technology. GPR uses electromagnetic waves to detect the reflected signal from subsurface, which is caused by difference of dielectric constant of subsurface material, such as rock and soil. The antenna is one of the most important elements of GPR system. The operating frequency of the antenna determines the ground penetrating depth and resolution image. It is well known that the low operating frequency can detect deprived subsurface objects, while the high operating frequency can yield high resolution for detection of shallowly subsurface objects. Generally, the frequency range from 300 MHz to 3 GHz is used for GPR application. as shown in the table. Therefore, the ultra-wideband antennas are required for the GPR system. Many ultra-wideband antennas have been developed for GPR applications, including horn antenna, Vivaldi antenna, bow-tie antenna, and printed slot antenna. It is found that the printed slot antenna can be a good candidate for GPR system due to its planar and simple structure, low profile, simple for mounting the system in both comfort and premium spec, such as under vehicle GPR system. Variant techniques have been reported in literature for miniaturizing the antenna size and improving the bandwidth of printed slot antenna, such as modifying shape of slot and stub, using an open slot, adding parasitic element on slot, using fractal structure, using double or trident shape feed line, and deflected ground substrate (DGS) at the ground plane. However, for GPR system, the back antenna radiator energy is not required for ground elimination. Therefore, the absorber and reflector are used to reduce backload and to form unidirectional radiation pattern. Research work 1 presents design of Copana waveguide phase bow-tie slot antenna for ground penetrating radar application. The bow-tie slot is modified, improved return loss, and reflector cavity is added to achieve direction radiation pattern. The maximum gain of antenna with reflector is 5.36 dBi. However, this antenna is quite low gain. Research work 2 presents design of an ultra-wideband directional antenna based on directional radiator and a multi-layer pyramid absorber. The multi-layer absorber are used to achieve a unidirectional radiation pattern over the entry frequency band. Although this antenna can provide good unidirectional radiation, but antenna is large and heavyweight. Research 3 presents wideband reflector back folder bow-tie antenna for ground penetrating radar application. The bow-tie slot is blended to improve impedance matching and to forecast the radiator power into both side direction. In addition, the banded antenna is backed with copper reflector in order to form unidirectional radiation pattern. The maximum gain of antenna with reflector is 12 dBi. Although this antenna can provide good radiation characteristics, but the antenna design is complicated and it is not simple structure. The objective of research are to design printed slot antenna with reflector for ground penetrating radar application. To design printed slot antenna operating in the frequency range from 0.3 to 3 GHz by using inexpensive FR4 substrate. To improve radiation pattern of printed slot antenna from bidirectional to unidirectional pattern by using reflector. Now we will move on to the antenna design. The geometry of the proposed antenna is shown in Figure 1. The antenna is printed on FR4 substrate with thickness of 1.6 mm, relative permittivity of 4.3, rod tangent of 0.025. The basic antenna configuration consists of an inverted U-shaped slot combined with rectangular slot, double-shaped feed line, and inverted U-shaped turning stub, DGS structure, and reflector. The reflector with the dimension of 260 mm plus 300 mm is placed behind the radiator to form directional radiation pattern. The reflector is made of one-side FR4 substrate. The separation distance of between printed slot antenna and reflector is set to quarter wavelength at frequency of 0.33 GHz. The optimized parameter of the proposed inverted U-shaped slot antenna with reflector are listed in Table 1. The antenna design procedure starts with an inverted U-shaped slot antenna without reflector. The design evolution of the proposed inverted U-shaped slot antenna is shown in Figure 2. This section is resolved. The proposed antenna is designed and simulated by using CST Microwave Studio. Figure 3 shows the simulated reflection coefficient RS11 and realized gain of different antenna structure. It begins with original antenna. It can be seen that the original antenna can obtain impedance bandwidth in frequency range from 0.3 to 3.58 GHz. However, the S11 of this antenna is poor at lower frequency, which affects impedance matching when placing the reflector behind the antenna. Therefore, the wide rectangular slot is added at the top of the inverted U-shaped and is named as N1. However, the impedance matching is still poor at frequency around 0.7 GHz. Thus, two rectangular slot DGS are cut at the bottom edge of the radiating slot and is named as N2. In order to enhance impedance matching at frequency near 1.2 GHz, the ground plane of antenna is modified by adding the round corner and it is named as N3. The antenna can operate in frequency range from 0.32 to 3.64 GHz with better S11 over desired frequency range. In order to produce a unidirectional radiation pattern of printed slot antenna, one of the common and simple methods is to place a reflector with an electric conducting surface at a distance of at least quarter wavelength under the radiator. Therefore, the reflector mesh of a one-side FR4 substrate is placed below the proposed antenna with separation distance of D equal to 230 mm or around quarter wavelength at 0.33 GHz. It can be observed that the reflector significantly affects the impedance bandwidth. The proposed antenna with reflector gives similar bandwidth as the proposed antenna without reflector, which can operate in frequency range from 0.32 to 3.64 GHz. Figure 5 shows the simulated gain of proposed antenna with and without reflector. The gain is mostly enhanced over the entry bandwidth when placing the reflector below the antenna. The gain is enhanced from 2.85 dBi to 6.49 dBi at 400 MHz. The maximum value of gain at 0 degree is about 9.1 dB at 1.6 GHz. It is seen that the main lobe of proposed antenna without and with reflector have tilt from Z-axis direction when frequency increase, resulting in the decrease of gain at 0 degree. However, the proposed antenna has a good directional radiation pattern over the frequency range from 300 to 900 MHz, which can be used for subsurface imaging. In order to confirm the unidirectional radiation pattern, the simulated front-to-back ratio of antenna without and with reflector are compared as illustrated in Figure 7. It can be seen that front-to-back ratio of proposed antenna without reflector is improved over the entry operating frequency when including the reflector. In order to validate the simulated result, the proposed antenna with reflector is fabricated as shown in Figure 8, and Figure 9 shows simulated and measured reflection coefficient of proposed antenna with reflector. It can be observed that the simulated and measured results show good agreement except to lower frequency, which is mainly caused by the fabrication error. The measured impedance bandwidth of proposed antenna with reflector cover frequency range from 0.33 to 3.59 GHz. Figure 10 shows the simulated and measured radiation pattern, including core and cross polarization in the XZ plane and YZ plane at frequency of 1 GHz and 2 GHz. The measured radiation pattern of proposed antenna with reflector are in good agreement with simulated result. The proposed antenna can achieve unidirectional radiation pattern. In addition, comparison between the proposed slot antenna with reflector and other slot antenna with reflector in literature is shown in Table 2. Although the fabricated antenna in 3 achieve high gain, but it is not low profile structure. In addition, this antenna operates at high frequency band. Therefore, the proposed antenna with reflector can achieve a quite high gain at low frequency while low complexity in design. Finally, conclusion of this work, the design of ultra-wideband inverted U-shaped slot with reflector has been presented. The reflector is used to improve the gain and front-to-back ratio. The proposed antenna can operate in frequency range from 0.33 to 3.59 GHz. The proposed antenna with reflector has a maximum value of gain at 0 degree of 8.86 dBi at 1.5 GHz. Thank you for your attention.
Thank you so much, presenters. And this is a time for question for the last papers. Any question from the audience, please? 1, 2, 3. Okay, I would like to ask some things. You did some antenna for the GPRS application, right? You got wideband and you got very high antenna gains versus the frequency. Very nice antenna. I would like to ask some things about the cross polarization. I thought that in your results, maybe figure 8, you got the cross polarization very strong polarization in the XC plane, okay, and also XC plane both for the A and B. I would like to ask something about the effects of the cross polarization to the GPR system. Can you explain to me?
I think that a reflection behind the antenna without effect cross polarization.
The first question is effects of the cross polarization to the GPR system. That is the first question. And the second question is why you get different from the simulation. Can you answer me?
Different.
Because the measurement or some things.
So.
Okay, don't worry about that. Okay, when you measure the U antennas, you use the standard linear polarization measurement system, right? I mean, you use the standard antenna, right? When you measure radiation patterns. It's okay. Don't worry about that. You can study more about the effect of the cross polarization on the GPR system, right? Because I get your, I thought the result, you get some error from the measurement. something like that. Okay, you have to improve the measurements results. Okay, for the next time, next paper. Yeah.
Okay,
For
thank
the
you.
last question for me, 1, 2, 3. Yeah. Okay, I have already asked you about the collaboration, and the last one, why you try to improve the unidirectional patterns property for the GPR. GPR require the unidirectional pattern, right?
Yes.
Okay. Can you explain more about that? Why you need the unidirectional patterns?
I use next research. I think I use vehicle in test soil rock reflect in soil in subsurface imaging.
Oh, okay. You focus on the ground, right?
Yes, ground.
Okay, you forgot on the ground. It's okay. Okay, is any question for the audience? We have, no time right here. Time is up. Okay, any question for the short questions? No? Okay, thank you so much for the speaker. Thank you so much. And I would like to conclude the session. Today's morning session, EM1OL, that already finished right now. And we just finished 5 papers, really nice papers about the antenna and fabrication, something very interesting application. Okay, I would like to say thank you to everyone here. Thank you to every presenter here. Okay, I would like to close the session right now. Thank you so much and see you next time. Thank you.
Okay. I introduce to myself. I'm assistant professor exit from Rajamangala University of Technology, Ratnakosit, and will be Mr. Chairman in this session for the antenna section. And the first paper is a broadband resonant cavity antenna using taper to identical layers metamaterials. Mr. Komsan is going to present this work. The presenter, can you present now?
Hello, this will present our research work. It's titled about band resonant cavity antenna using trapper to identical layer metamaterial. My name is Komsan Kanasit. I'm with College of Computing Brains of Songkhla University, Phuket, Chapat, Thailand. My co-author Thirapat Jariya. He is with Faculty of Engineering, Kasetsat University, Bangkok, Thailand. The outline including background of the RCA, in short, it stands for Resonant Cavity Antenna. Then we give you a review of conventional RCA, broadband RCA with a non-uniform structure. The proposed structure and characteristic result are provided is end with the work summary. Let me start with the background of the RCA. The left-hand side figure shows you a basic physical structure. They are including with the 2 surfaces, one called PRS, it stands for partially reflective surface. Other one is ground, is the total reflector. That is separated by a Hess parameter denoted for the distance, resonant distance. The source antenna can give a primary radiation its position inside. We can understand the mechanism with a ray. So start with the source and radiate inside the cavity at a reflection. And then you can see a part of ray or field can transmit through the surface, this surface PIS. That is become a superposition when it's satisfied with a particular frequency that can enhance the bond. Radiation can gain the energy and the radiation at the bond side. To consider the analysis, the right-hand side shows you a formula that is 3 terms. One is the phase of the PIS, second one is the phase of the ground, and the third is can represent the travel trip phase. It depend on the distance here. or is satisfied as the multiple to pi when and represent the integer. For the directivity, can figure out using the reflection magnitude here. The note here, PIS can be a reference relative surface or dielectric layer, and also ground surface can be a PC and MC that is different in the reflection phase. Look at the review here. That work is quite I think it's popular to study. It's back to 1956 here. The percentage cheese over the aperture can give the board side radiation that is high peak at the pattern. In 2001, this work really with the dipole stick pack on the board foam here in front of the work guide. The gain can more than 20 dB at the around 14.3 gigahertz. In 2006, that is the key work idea to make the broadband cavity antenna. Look at this figure. It come up with double layer or two layer in different sides of the patch. To analyze the unit cell simulation reflection response can give the unique, it's called positive gradient, that is can occupy the phase specified over the band or adjust frequency. This work it can start 13.5 till the 14.5 at the 20 dB. And then more work is the 2014. The 3-year also represent that is 3 balls with different size of the path. To study unit cell, give this one. The response is linear response here. The 1 layer, 2 layer give the feature of positive gradient. And then we can extend more of the response here. The operation here start from 19.5 is end with at the 15.5, that is 20 dB, and upper end with the 19 dB here. In this work, they present the two layer as well, but in more detail, it's identical layer. It's not show up about the positive because here we show up about the response of the transmission. This gives you a resonance at the target response 10 GHz. To model the cavity is come up with the lower and upper, and when implementing the antenna structure that is come up with the broadband start 8 to 12 GHz, that the peak is allowed at the 12.5 dB. More study use the rigid dielectric FR4 that is lossy structure is make the response the same as the gain start at 12. The peak is allowed at 15 dB. More study about the field size superstate with 4 by D till 9 by 9. We can see when increase the aperture size or array size, the decoration show up at the middle band here, and the field study also study and see the board size is decreased here when we increase the aperture array size. Apart from that, the taper complementary surface also giving here that double layer with the circular pad and the circular aperture on the metal sheet, and also the primary antenna with the aperture with the pads working here. This work gain at around the 16 dB. More than that, we have a look the keyword as well. That is come up with the concept we call taskword probability gradient. Look at the superstate, the gradient of probability are changed along the super state. And this spot it could show you is quite interesting, the wide gain bandwidth. And also this another key idea to talk about phase identifying transparent superstate. That is two layers of the superstate. One here is uniform and other one is non-uniform. The gain is input show up here. In this work, I will give you two factors in consideration. One is state of parameter of the aperture size, that we know that the large aperture is not support the bandwidth. And second point, we talk about the effect and diffraction in the superstate due to the primary source is not a period that is produced the polarized waveform that is can be any arbitrary of incident phase. And also at the diffraction at the gates can dominate the surface interference. This slide shows you the proposed configuration at this figure. The physical figure is two parts. One on the top is superstate that can see the cavity inside. It can refer to a micro machine structure using a thin film that is represent the LCP or liquid crystal polymer, and we can use the PMMA is kind of the acrylic polymer to make the limb here or spacer, and also the same method for the primary source aperture with a couple pads here. On the top, you can see a trapper structure here. Inside is the L1 square feet 3x3. Emitter is L2 is smaller, and the outer is the smallest size, is represented by L3. The aperture with the short CPW or coconut waveguide apply here with the exciting port or connection here, and we provide the road path with the rectangular shape. The optimized size is limitable. You can see this is a superstate with the period 7 millimeter. L1 is inside 6 millimeter. Individual L2 is 5.5 millimeter, and the outer is 5. That is optimized based on parent study to make the better response. The SC is 21 millimeter, is differ halfway at the lower frequency response, and S is represent the thickness superstate, and P is a path separation here, that is 4 millimeter and 2.5 millimeter. The path resonance is come up with the resonance is 11 millimeter and 20 millimeter. The gap of the feet here to 0.2, and the width is the 1.4. We study the response of individual unit cell for path size. The first path size can see the transmission resonance, and it is a reflection response. For the first L1 is resonance is show up at the 10.84 GHz. The second one 12.06 GHz, and the third one here is 13.1 GHz. To decrease the size, is make resonance is higher, and the transmission is more broad. You see here. This is a phase response. See the diffusion phase at the lower side of here. It can specify with the cavity model, and this phase transition and phase shift for each of them show at the resonance. To characterize the antenna, we show you to respond. The left hand side is the antenna reflection. It can work at the 8 to the almost 14 GHz, and the left hand side show you a gain response. You see the boss band can show you in the back curve. That is so risk is our work compared with the That's right here is a uniform version super state, right? Can get more bandwidth here, around 6%. For the left is a comparison in case of the this one in case of the without super state, the solid line here. You can see the improvement with the super state over the band is improved around 6 dB. Another one is without the cavity without the pad loading here. You can see the gate are dark at the middle and we get to peak at the 8 and 11 gigahertz here. That is can prove that we have the benefits or the keyword to extend the bandwidth of the radiation and improve the gain radiation compared with the primary source. This slide show you the pattern that come up with the directive pattern both of the E plane and the H plane. We select the particular frequency as 10 gigahertz to show you. And we see the beam width are different for lower to the upper here. And also the simulation here show you animation of the field here in E field at the E plane. You can see it is the E field at the gap between path, both of them. And then there's a head field that can make clear the field uniform can be in the trap structure. There is uniform structure we can under smooth in here. I can show you the animation to show a response of the field, head field here, right? Over the structure, you can see the uniform, and this is a uniform path. Is not the spot is not uniform in size. At the end, I would like to summarize the work here. We propose 3 steps by 7 array and improve 6% in compare with the uniform. The second point, resonant cavity can contribute from the transmission resonance that is shown in the cell study, and the effect can overcome the field incident at the site, the edge site. And the benefit in this study I can show you that material can use for step the micromesh structure give less dielectric material, simple structure giving in this work, and also the feeder partner provide in the partner phase. Thank you for your attention.
Okay, thank you for your presentation, Mr. Komsan.
Yes.
Any question from in this presentation? Any question for this presentation? Okay. For me, I have a question about your work. And almost you have done our simulation. How about the fabrication? Have you make it?
For this work is not just for fabrication prototypes, but we have done for the uniform version that is contributed in the journal in a couple years ago that we reviewed in the presentation as well.
Okay. Have you planned to make it or didn't
Yeah,
have?
it's a future work to more study about the effect of the tapper response, because if you see the response, we try to gain more about the quality of the peak at the both side, and compare in the sum of work, they achieve more data able to improve the work to gain more by using the more array size and more steps. Like this work, I spent 3 steps. I can study 9x9 with the 5 step or 6 step and study the repetition of the aperture size. That is our future work.
I have seen in your structure is macro machine structure, and I worry about when you make it. It's not easy to make.
Yeah, luckily in the previous work we can achieve that step, but in the process it's not simple. We need to be careful to make. I use the simple one because due to the LCTP film that is can make it like a thin substrate and use the air cavity that is used acrylic or PMMA or using the laser cutting to make a spacer, right? And we use the some adhesive process to assemble them together.
Yeah.
Yeah.
Okay. I hope that it will successful.
Okay, thank you, Chairman.
Okay, thank you presentation for Mr. Komsan. And for the next presentation is the paper title is Ultra Wideband Fabric MIMO Antennas for Future 5G Application. The presenter, I'm not sure. Mr. Can you introduce? Punjalit, okay. Please start your presentation.
Hello, good afternoon, everyone. My name is Punjalit Kumkhet. I will present ultra-wideband fabric MIMO antenna for the future 5 generation application. The content of this paper is introduction, literature review, antenna design, result and discussion, and conclusion. Introduction. Today, high-speed wireless communication is critical component in the development of the variety of industrial, include agriculture, transportation, and public health. Ultra-wideband communication is a transmission method that offers a wide band of the high-speed data transfer while consuming little power and allowing communication over short distance. And the 5G technology is the wireless communication technology that offers high-speed data transmission with the lower bandwidth than ultra-wideband, but it data transfer over longer distance than ultra-wideband. This is position of this antenna. Literature review 1. Ultra-wideband CPW feed 4-port connected ground MIMO antenna for sub-millimeter wave 5G application by Ahmed Patel and team. This is show design of the 4-port MIMO. It feed by CPW on the circular pad. This is show S parameter of the antenna. Literature review 2. Investigation design of the enhanced decoupled ultra-wideband MIMO antenna for variable application by Ahmed Balande and team. This paper is the interesting of the antenna because of the antenna is installed on variable application. This paper use conductive antenna, use the copper pad and install on the substrate fabric. This paper is show enhanced decouple by the S-stub, 2-stub. The red line and back line. This show 1-stub and blue line and green line show 2-stub. In this paper, it show installation on the phantom body and body human. for this paper is combined two literature review for the design antenna. This antenna designed by the conductive material EMC, EMI, copper, nickel, coarse polyester fabric. Characteristic of the material is frequency response 10 MHz to T plus GHz. Temp range minus 40 Celsius to the 150 Celsius and up to 200 Celsius short term. Thickness 0.114 mm. Surface resistivity 1 ohm per square. This material is fixed sticker. You can use iron for the install on the fabric. Substrate material is the polyester fabric. Characteristic dielectric constant epsilon r of the 2.25 and thickness of the 0.40 mm. Loss tangent of 0.009. This antenna design one antenna by the formula 1 and 2. This is parameter of the antenna for after tuning. This antenna combine antenna 2 antenna for the design MIMO antenna by the formula 3. The S parameter is show tuning parameter T for the decreased isolation of the antenna 1 and 2. This is parameter of the MIMO antenna in this paper. The result and discussion. The antenna is designed by the half circular and half hectagonal by feed by CPW. It is show prototype of the ultra-wideband fabric MIMO antenna in this picture. The result and discussion. A parameter of the antenna is cover length 5G midband of 2.6 GHz and ultra-wideband T.1 to 10.6 GHz and 5G high band 26 GHz. This show isolation antenna 1 and 2 is lower than minus 20 dB. This show ECC correlation of correlation coefficient should be less than 0.05 and group delay should be less than 2 nanosecond. This picture shows radiation pattern of the antenna on the frequency 3 GHz on the copolarized X-axis. It shows radiation pattern of the antenna is omnidirectional and 7 GHz it show the light omnidirectional and 11 GHz it show right omnidirectional same. Gain of ultra-wideband fabric MIMO antenna it show frequency on the frequency 2.4 is 2.73 dBi and 2.6 3.19 dBi. 3.5 is 3.67 dBi and 5.5 is 4.40 dBi and 7 4.26 dBi and 11 3.35 dBi. The last 24 is 4.62 dBi. The conclusion: the ultra-wideband fabric MIMO antenna has a simple structure that enables it to flexible and install on the curved surface. The antenna achieves approximately 175% bandwidth 2 GHz to 30 GHz. The antenna designed to cross to MIMO antenna by EBG technique that isolation between the element is better than -20 dB. The antenna radiation pattern are like omnidirectional and average gain of the 3.75 dBi. This demonstrates the suitability of the post antenna for the 5th generation MIMO application. This antenna propose comparison of the literature review on this paper. Thank you for watching. Any
Hi. Thank you for your presentation, Mr. Bunyarit. Any question in this presentation? Okay. And for me, I have a question about this. And your work looks good and very good. The frequency response and S11 is given below -10 dB. I want to know that have you do the measurement for the antenna gain for the overall band? The range is 1 GHz to 30 GHz.
antenna gain I measurement on the 2 GHz to 30 GHz average 3.78 dBi.
dBi, okay. And I haven't seen in the paper. You can push the graphical of the frequency gain response of this antenna. It's really good. And have you test author like your movement fabric antenna, or is Ben's allowed antenna? The gain is will be changed or something like that.
Now I can note measurement on the visible and the measurement gain same time. I demonstrate of the flexible area for the test flexible antenna for the test efficient effect for the curve area on to the antenna now.
Oh, okay. I mean, I demonstrate the material for the curve area for the install this antenna for test. Okay. I have students who doing like this, and he tests like is where in the cross and movement and check the response and gain too. It's like a practical work. Maybe you can do it in the future. Okay.
Yeah.
Okay. Yes. Thank you. Yes, thank you very much for your presentation. For the next presentation is dual chip UHF RFID tag antenna for distinction of movement direction. The presenter who will connect Mr. Okay, please present yourself and present your work.
Hi. Firstly, I would like to thank you for providing an opportunity for sharing the research entitled Dual Chip UHF RFID Tag Antenna for Distinction of Movement Directions. My name is Javadali. I am from Thai German Graduate School of Engineering KMUTNB, and these are the contributing authors of this research. So the layout I'm going to follow during the presentation will start with introduction, goes with the literature and purpose of study. Also we'll discuss about the adopted methodology, the design, and finally we'll end up with the conclusion. Nowadays, Thailand is a connecting hub for accessing ASEAN, Cambodia, Laos, Maldives, Vietnam, and Eastern Economic Corridor markets, and that is why 34.2 million travelers have shown their confidence towards the MICE industry of Thailand, based on which Thailand Convention and Exhibition Bureau is focusing more towards to provide a quality of services and also to meet the industrial 4.0 vision of Thailand, based on which indoor positioning system is one of the basic requirement to provide the quality of service. But it does not only provide the quality of service, actually it also provide an insight about the stakeholders, and it uses wireless technology such as Bluetooth and other IoT technologies such as Wi-Fi and RFID technology. In order to provide an accurate, economical, and reusable system, radio frequency identification is nowadays in demand, and not because it is a low-cost technology, but also it provides an easy digital labeling. It was first introduced in 1983 by a scientist named Charles Walton, and it utilizes radio wave to identify and track the objects. The main components of these technologies are the tags and the readers. The tags are basically consist of the antenna and the chip embedded on them. There are two categories of tag: the passive tags and the active tags. The passive tags are actually get their energy from the signal that is coming from the reader and send back the information contained in it towards the reader. While for active tag, we need external source such as batteries to send the information to the reader. Other than easy deployment and cost effectiveness, the other advantages of this technology over conventional barcode and QR codes are reading that it reads over a larger distance. It has high data storage capacity, and it can read multiple tags at the same time. Furthermore, it also helpful in providing positioning accuracy, mainly because of the information contained in this technology, such as angle of arrival and direction of movement and the main beam estimation. So the conducted literature for localization and detection of movement reported the technologies like the use of multiple readers, sometimes dual readers or antenna array in the multiple readers, and also the optimization of RFID waveforms at the reader end. So basically, all reported technologies were more focusing towards the reader technology. Since the literature study more focused on the reader technology, and the purpose of this study is to determine the direction angle using a tag antenna diversity. So in which we will have a single tag consist of two antennas and two chips embedded on those antennas. So we call it a dual chip tag technology instead of a multi-reader technology. In this technology, we will use a beam splitting using a reflector between the tag antennas, and the tag movement direction can be detected using a single reader. So in this way, we are offering a more cost-effective technology as compared to using multi-reader technology. Therefore, the basic idea of this technology can be observed using this prototype, where we have a single reader antenna that have been installed over a rooftop in an indoor environment, and a tag consisting of a dual chip antenna. And to achieve the beam diversity, and a reflector have been placed in the middle, and the antenna have been installed over the top of a moving object such as robots or moving vehicles to basically implement the localization concept. To implement the concept, two microstrip dipole antennas embedded with the two RFID chips, that in this case is NXPU code G2IL with a complex impedance for the feeding purpose has been used, and both of the antennas have been placed over a substrate called FR4 with the dielectric constant of 4.3, and the mid reflector has been embedded between the two in order to get the beam diversity. And thereafter, to implement the concept of a moving object, that a tag has been placed over a reflecting surface. This table is basically representing the overall dimensions that have been achieved, and in our case, the dimension of the achieved antenna is 128 into 65 millimeters. Thus, after performing the parametric study, the finalized results are shown in this slide, where from the reflection coefficient, it can be seen that the achieved bandwidth is from 906 megahertz to 923 megahertz, and that is basically more than 5 megahertz of the bandwidth in which is usually required by RFID for its operation, and the tag isolation in this case is minus 9.1 dB. Therefore, to observe the beam diversity, the radiation pattern has been plotted for the simulated antenna, and from this plot you can observe that both of the beams are back to back at an angle of 90 degree for left and right antennas of the tag, and it can also be visualized in a linear plots. In this case, we have plotted for the highlighted left half of the tag, and from this you can observe that angle extraction can be possible, which in this case is 90 degree by using a gain difference, and the gain in this case is 3.8 dBi, while the efficiencies are 56.84%. So to visualize the concept of a moving object, and also to elevate the beam angles obtained in the last slide, the antenna have been placed over a reflecting surface by considering moving objects such as vehicle or a robot top covering to basically observe the results, and the spacing between the tag and the reflector back reflector has been determined based on the maximum gain achieved. However, the bandwidth in this case is from 910 megahertz to 933 megahertz, which is once again more than the required 5 megahertz of the bandwidth for RFID to operate. Thus, once again, to observe the elevated beam angles, the radiation pattern has been plotted, and from the figure, you can observe that the angle has been elevated up to 21 degree in case of antenna 1 and antenna 2 of the same tag. And once again, the linear plotting to observe the gain difference and to provide the information that can be helpful in angle extraction is plotted in this graph, and the efficiencies in this case is 35.67%. The reason of having a low efficiency is basically the use of the electric loss, and also since back reflector is contributing more towards the loss, so this is one of the reasons of providing this low efficiency. Therefore, in conclusion, a multi-beam dual-chip UHF RFID tag antenna has been proposed in this study. Two beams oriented back to back at an angle of 90 degree for left and right antennas of the tag has been observed, and to elevate those beams, a 20 cross 20 centimeter square reflecting surface has been used, and the beam angle achieved in this case is 21 degree with the bandwidth of 17 megahertz without having a back reflector, and 23 megahertz with having a back reflector, which is as I already mentioned earlier, that is more than the required bandwidth for an RFID to operate, and the efficiencies in this case is 56.84% and 35.67%. And the reason I have already mentioned that the use of use of lossy and substrate is basically contributing towards this low efficiency. And once again, the back reflector has added more losses to this one. So for future, we will be considering the low loss substrate, so that we can improve the efficiency as well as we can control the beam angles, so that it can be used for more directive applications in the future. Finally, we would like to acknowledge King Mongos University of Technology and National Science and Technology Development Agency for supporting this work. That's all from my side. Thank you for paying attention. I'm now open to your questions.
Okay, thank you for your presentation. Any question in this presentation? For me, I have a question. I interest frequency response when you are sharing the gap between the dipole antenna and the reflector. I want to know that why is the gap between antenna and reflector is affect to the frequency response of S11?
Actually, it did respond. It did affect the S11 a bit, but mainly it affect the gain factor in that case. So what we did is we actually focused more towards the gain. So that is why we choose a suitable distance between the reflector and the tag, so that we can keep it.
Normally, if it's very close, I think that it should be give the very good matching of the antennas. I thought that it's because of the resonant frequency
between two antenna, I mean, a reflector and antenna, and it's like a mutual coupling between them. And if it have a good spacing, it will be work together. But if you are very close, it may not going work to work it. Okay, it's good. Okay, thank you for your presentation. Mr. Yauti Ali. For the next presentation is the compact Pranas monopole antenna switch 5.5 GHz band notching. The presenter is here.
Good morning, ladies and gentlemen. Let me introduce myself. My name is Chumphorn Sunthorn. I'm Master Program Student in Electrical Engineering at Rachamankala University of Technology, Lana, Chiang Mai, Thailand. Today, I represent my group at the conference. I would like to present compact Pana monopole antenna with 5.5 GHz band notching. The aim of this presentation is to expand band notching design technique applied to the ultra-wideband antenna. I have divided my presentation into 5 parts. I will begin with an overview of this research. Then I will move to all literature review. Next, I will mention antenna design. After that, I will focus on the implementation and the results. Finally, I will go to talk about conclusion of this study. I will start with some general information on ultra-wideband system. The ultra-wideband system has a wide frequency range from 3.1 to 10.6 GHz. There are more advantages such as compact size, high data rate, and low power consumption. The wireless device have small size and consume low power. Therefore, the printed monopole antennas are suitable to use for ultra-wideband device. Because of most printed monopole antenna are low profile, small size, low cost, easy to fabrication, and easy to design. Due to the frequency range of ultra-wideband system is very wide, the electromagnetic interference that Wi-Fi and WiMAX frequency band may be occurred. To reduce this problem, ultra-wideband antennas could be designed with band notching. As I said at the beginning, to the printed antenna with compact size and various shapes with use design for frequency rejection such as Task 1. Design of printed ultra-wideband monopole antenna. The antenna design using unitary semicircle, trapezoid, and triangle shapes. Frequency from 2.95 to exceed 11 GHz. The height of antenna is 35 mm. Task 2. Design and implementation of ultra-wideband slot loaded printed antenna for microwave and millimeter wave application. The antenna design using asymmetrical U-shaped slot. Task 3. Design of 5.5 GHz band notching for printed ultra-wideband pentagonal monopole antenna. Show 3 techniques band notching of 5.5 GHz for the printed ultra-wideband by embedding narrow slit, including invert C-shape and invert open N triangle shape into the pad. Frequency range from 2.8 to 10.55 GHz. The height of antenna is 36.58 mm. Task 4. The printed slot antenna with built-in filters for band notching can operate triple band frequency. Task 5. Printed ultra-wideband antenna with 3.5 and 5.5 GHz band notching. The antenna design using embedding in inverting L, invert L shape, and modify U-shape narrow slit into the monopole pad. Can operating frequency from 2.8 to 11 GHz. The height of antenna is 34 mm. According to literature review it will be applied to design the antenna with 5.5 band notching. Now, I'm moving to the next topic that's about research study. For ultra-wideband antenna is designed. The figure 1A show baseline antenna and the figure 1B show modified pad. We modify pad by cutting the top baseline antenna to pentagonal shape. The overall structure of proposed antenna will be presented on the next slide. The characteristics of proposed antenna are a single metallic side FR4 substrate with the thickness of 1.6 mm, relative permittivity of 4.4, and loss tangent of 0.0019. The height of proposed antenna is 34.5 mm, which is smaller than baseline antenna. For 5.5 band notching frequency design, the proposed antenna will be L-shaped embedding by both sides of patch. You can see that figure 3 in slide. The overall length of the L shape is a half guide wavelength of 5.5 GHz. The position of L shape on the pad is one parameter of research study. Another parameter study will be described to next step. This slide we study L1 and L2 parameter. The figure 4, when L1 increase, the frequency of rejection is shift down, and L1 decrease, the frequency of rejection is shift up. The figure 5, you can see that when L2 increase, the frequency of rejection is shift down, and L2 decrease, the frequency of rejection is shift up. The figure 6, we using P1 as 16.5 mm because of appropriate of notch band at 5.5 GHz. The figure 7 show the parameter L1, L2, and P1 for control the notch bandwidth. When we fix parameter P1 and vary parameter L1, the overall length of L-shaped narrow slit L1 plus L2 is maintained with is equal to half guide wavelength of 5.5 GHz. So you can see the bandwidth of band notching is controlled by expanding L1 parameter. This slide shows a comparison between the baseline antenna and the prototype antenna. As shown in left slide, which the prototype antenna is smaller than the reference antenna. And the figure 9, the simulation computer program by CST and CLAN. The simulation results are similar at 5.5 GHz. While the measurement result, the notching frequency length of 5 to 6.5 GHz is bigger than simulation results, causing from the fabrication fault. The radiation pattern at exact plans is similar to omnidirectional pattern at low frequency and more distortion at higher frequencies. The radiation pattern at YZ plan is similar to bidirectional at low frequency and higher frequency. More distortion will occur when the antenna operates in higher mode. This slide shows time domain and gain measurement results. The broadside gain is down at frequency band rejection, and the proposed antenna is not working at this band. The group delay at frequency band rejection is discontinuous, with the design antenna cannot working at this band. In conclusion, Let me sum up my main point of the presentation. First, the compact printed monopole ultra-wideband antenna with frequency band of 5.5 GHz rejection. Second, by using two L-shaped narrow slit with overall length approximately a half guide wavelength at the rejection band embedding into both sides of the antenna pad band knot. Finally, the proposed antenna can be used for the ultra-wideband systems with electromagnetic interference elimination at Wi-Fi and WiMAX band of 5.5 GHz. Before I end, I would like to say thank you to Wireless Communication Research Group for measurement results and software simulation. Thank you for your attention.
Okay, thank you for your presentation. Any question in this presentation? I have a question about your work. I seen your measure radiation patterns of your antennas and has many noise around of the shape. I want to know that the reason why is there has many noise show the radiation pattern.
Excuse me, Sharon. Excuse me.
Okay, can you hear me?
I'm teacher become the second usher.
Okay.
This of the radiation pattern at high frequency show many noise, right?
Yeah.
I think maybe occur from when the rotation of the turntable. I think maybe the noise may be caused to the pattern at this frequency. I think that.
Okay.
I don't, because the radiation pattern are measured in the chamber room.
I used to got this problem before. It's like it's not good in calibration for when you start, and the problem is it's not a chamber room only. It's like some frequency going to inside the room, and you may check the specification of the absorber. It can be cancel the frequency around of the antenna, and also the range of the antenna test and your proposed antenna. It should be have a good spacing. I mean the range of when your measurement you can test for the like a calibrate for the for direction like a 0 degree, 90 degrees, 180 degree, and 270 degree first, and check if it's okay. You can turn around.
Okay.
Or many points is will give the problem too. You can use some program to make interpolation of this to cancel this noise. It's like noise cancellation for this to suggest one.
Okay, thank you.
Okay.
I think that's
okay. It's finished our presentation. I want to have a group photo for in this room. Please open your camera and take photo together or finish this session. Okay. 1, 2. Okay. Thank you. Thank you for presentation for everyone. This session is finished. Okay.
Thank you, Chairman.
Thank you.
Thank you.
Goodbye, Chairman.
Bye. Goodbye too.
Thank you. Bye bye.
Bye bye.
So hello, the participants of the session. My name is Suramesh Chalermvisutkul. I am serving as the session chair of this final session of the electromagnetic track. So the session will start 3:45 p.m. So we have 3 minutes left. So we'll wait so that we can start on time. So I will mention the topic of each presentation, and I would like to ask the host to play the video after the short introduction. So this is the way it should be. And so about at the end of the session, we will have a virtual group photo together. So at the end, I would like to ask all the participants and presenters to turn on the camera so that we can take the virtual group photo. Okay, there are still 2 minutes left. All right. So the first presentation is titled An Experimental Study of Effect of Dielectric Materials on Wireless Power Transmission at 6.78 megahertz, and the presenter will be Professor Kitisak Phaebua. So, okay. All right, so the presentation is now started.
Good afternoon, ladies and gentlemen. My name is Kitisak Phaebua. I'm come from Kimagut, University of Technology, North Bangkok. Today, I would like to talk about my research work in the title of An Experimental Study of Effects of Dielectric Material on Wireless Power Transmission at 6.78 megahertz. For the next one, these are my contents. And I have the introduction for the first one. And also the next one, I would like to talk about the objectives. And also I will describe the deep detail about the theory and its system designs, consists of the system designs, experimental scenarios. And the next one, I will show the results. And finally, I will conclude my work. And let's see here, introductions. You can see this is the commercial application of the power transmission. And this is we applied for charge the cell phone. You can see they have the transmitter pass right this, and they have the receiver in the cell phone, and they can transmit the power wirelessly by using the antenna, by using the electromagnetic wave. And electromagnetic wave will be traveling through the air from the transmitter pad and go to the receiver right here. It is the first application, commercial application of the wireless power transfer. This is a QI standards. And the QI standards use the power around 5 watts and also use the frequency around 110 to 205 kilohertz. For the highest power standards, that is the medium power QI chargers. They use 80 to 300 kilohertz, and with the powers around 120 watt. That is the commercial application of the power transfers. And you can see, I want to talk about a little bit about the theory about the power transfers. And for the power transfer, we have we can categorize into 3 categories here. We have the electromagnetic inductions that we use nowadays. We use the QI standard, and also we have the magnetic resonance couplings that provide the very long range for the power transmission. And the next one, we have electromagnetic radiation or we can call the microwave methods or laser beam methods. Okay, and the next one, and the third one, electrical conduction, is really dangerous because we send the electric charge by using the high voltage. Okay, today we're going to focus on the first and the second method. And this is the objective of my work. I try to experiment the power transfer path through the dielectric materials. You can see in this picture, you can see right here is my experimental scenarios. I have transmitter here. I use 6.78 megahertz 5-watt transmitter, and we have the TX coil antenna here on the left-hand side. And also we change the dielectric material in between. Okay, we have the lightweight concrete blocks, and we have the high density wood, and also we have the fresh water. And at the right-hand side, there's the RX coil antenna right here. And also we have the receiver circuit to convert from the AC to the DC, and we have the MILO to evaluate the power transfer. And you can see right here, the next one. Before I go to the detail, I would like to talk about the system. My system consists of the power supply transmitter with the frequency around 6.78 megahertz. And also we have the antenna here. We have capacitor to match the resonant frequency. Okay, and the next one at the receiver, we have the RX antenna, and we consist of the IXL, and also we have the I have the capacitor to match the frequency resonance, and also. And we have the DC, AC to DC converter, and we have the load right here. And also, why we use the E-class power oscillator, because it provides very high efficiency. You can see in the green line here that if the class A provide very low efficiency for the class A. For the class B, provide the efficiency around 0.5 to 0.8, but for the switching mode, class E amplifiers provide very high efficiency. This is why we use the class E power oscillator. For the next one, the basic class E consists of the switching, and also we have the L matchings and also capacitor matchings. You can see right here. For the right-hand side, that is the prototype that we use for this work, and also the bottom one picture here, that is the frequency response of the circuit. You can see the maximum is 6.779 megahertz, very close to the desired frequency. Okay, the next one, I would like to talk about a little bit about the antenna design for this work. Antenna design is like you can see in this picture right here. The parameter of the antenna affect the performance, because for the magnetic resonance techniques, we need very high quality factors. High Q provides high power transmission. Okay, and how to get the high Q? You have to keep the spacing about around 2 multiplied by the diameter of the Y. Okay, let's see this chart. You can see it right here. If the spacing is really small and the resistance of the coils go up, okay, you can see right here. You have to keep around 2 times of the diameter of the coil. You get very, very high Q antenna. And also in this picture, left-hand side, this is my antenna that I use in my experimentals. You can see right here. Okay. For the next one, talk about a little bit about the receivers. I use the bridge circuit because it provides very high efficiency. You can see right here, the bridge capacitor provide around 92.3% power conversion. You can see right here. And also, and this is the picture of the diagram of the receiver. We have the RX antenna. We have the bridge circuits right here, and also we have the charging circuit right here. Okay, for this slide, I try I will talk about the experimental scenarios. For the first one, I will study the lightweight concrete blocks. You can see right here, we installed the RX coil in the left-hand side. We have the voltage meter and current meter to measure the voltage and current at the dummy load right here. And also we have the power meter to measure the power at the transmitting part. And also we have TX coil on the right-hand side. And also we have transmitter right here. Okay, let's see the results. You can see for the lightweight concrete box with the difference thickness 14 and 21 centimeter. And you can see the power input is 5 watts, and we got power receiver at the receiving power at the dummy loads is around 2.78 to 4, and in the case of the thickness around 21, we get very low because the separating distance is very large. You can see we got just 0.645 watt, really low. And for the next case, this case we use the high density wood to experiment the rate power transfer. You can see right here, the RX antenna, it is on top of the wood, and the GX antenna underneath. Right here, we have the voltage and current meter to measure the voltage and current at the dummy load right here. And also we have transmitter, and also you can see we have the power meter for the transmitter here. Okay, and let's see the results. For the high density wood with the thickness, different thickness 14 and 21, the P loads or the power at the receiver or the power at the loads, okay, is around 2.8586. And in the case of the thickness around 21, we get really low, 0.8204 watt. It's very low. For the next one, the last case, we did for the fetch water. We have fetch water in between GX and RX transmitter antenna and receiving antenna here. And also we have the power meter, the same things. We have the voltage and current meter to measure the dummy load, the same things, okay? And we change the thickness of the fetch water from 14 to 21 centimeter. And also we measure the power at the load. We got around 2.3668 watt for the thickness around 14, and for the thickness around 21, we got very low power, 0.3267. That's very low. Okay, for the conclusions, for the results, take a look at this table here. We have 3 different kinds of the materials. We have the lightweight concrete block, high density wood, and fetch water with the different thickness. We got the different power at the loads. Okay, and for the 14 case, for thickness 14 provide very high power transfers, around 50%, something like that. And we found that the high density woods achieve the maximum power transmission. And fed water provide very high loss, provide very low power, okay? Because we lost some things, we lost the electromagnetic energy, okay, in the water. Finally, it is possible to transfer the electrical powers through the electric materials by using the pilot power transfer technologies. Thank you so much.
Right, so we have time maybe for 1 or 2 questions. So any question from the audience? Okay, so if there's no question, I have one. So what is actually the mechanism of the loss? Because in my opinion, so the loss in dielectric is caused by the electric field and not by the magnetic field, which is the major contributor of the wireless power transfer. So
Okay.
can you comment on this?
Okay. I think the sort of the loss conforms maybe the matchings mechanism, something like that, because we put the antennas attached to the materials. Sometimes the waters and concrete blocks affect the resonant frequency of the antennas.
Yeah.
That is,
Okay.
I think that is the reason, because the low
Okay.
frequency, the loss in terms of the loss inside the material, for example, fresh water is not too much. But I think the reason that is the matchings. Yeah.
It's so it is detuned, if I could say that.
Yes.
Okay. Okay. So would be nice to see a proof that it is in that case. Yeah. So
I think if we have the automatic matchings, it's gonna be better. Yeah.
I see. Okay. Any other question? Maybe one short question, if somebody would like to. Okay. Yeah, I mean, a simulation would be also nice to see so that maybe we can recognize what is really happening inside and so on.
Yes, thank you.
Yeah, okay. Thank you very much. Yeah, okay, still I have one addition. So we have seen the distance of 14 and 21. What would happen if we have a shorter distance? Do you think that the loss difference of the three cases will get less?
Okay. If we decrease the distance more and more, maybe affect to the matching condition also. And we have to optimize when you move, we have to optimize the matching condition of the system also.
Yeah.
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 But if you move closer, TX and RX closer, you get very, very strong couplings between the TX and RX antenna, but affect a little bit the matching condition. Yeah.
Yeah. Okay. What is actually the optimized distance in the air in this case?
I suggest that you have to optimize everything in the real scenarios, I think.
Oh, okay.
Yeah, for example, if you try to send the power path through the wall, you have to optimize everything inside in the real situation. Yeah.
Okay. Thank you very much.
Thank you.
Yeah, so thank you, the presenter. So we'll move to the next presentation, which is titled Electromagnetic Property Characterization and Sensing of Endothelial Cells Growth Medium and Dubelco's Phosphate Buffered. So the presenter is Kun Rungrat Virattikul.
Hello everyone, my name is Rungrat Virattikul from King Mongkut University of Technology, North Bangkok. Without further ado, I'd like to present the proposed topic called Electromagnetic Property Characterization and Sensing of Endothelial Cells Growth Medium and Dubelco Phosphate Buffer Saline Solution for in vitro culture. Let's get started. This is the outline that I'm going to talk today. Started from introduction, system configuration, experimental validation, and conclusions. Introduction. Biological samples derived from patients or extracted from in vitro models have specific and very heterogeneous chemical profiles, which can be analyzed by several techniques. Example, dielectric spectroscopy. Water-based liquids such as buffer solutions and media are used to support in vitro cell culture. For example, to study pathogenesis of cardiovascular. In recent years, the measurement of permittivity and dielectric properties at microwave frequencies has been applied for untargeted characterization of biological fluids and measure the density of different cells in suspension. identification of frequency-specific characteristics of liquid samples with different chemical composition is particularly interesting, since it is the key input for sensor design and can expand our understanding of the physical characteristics of liquids over different ranges of frequency. A common approach for characterization liquid is to utilize an open-ended coaxial probe with its end submerged in the sample, which allows parameters to be derived from vector network analyzer measurements. System configuration. The three liquids, which are deionized water, endothelial cell growth medium, and Dubecos phosphate buffer saline solution, or DPBS, were investigated in reflection coefficient using an open-end probe in their liquid samples, and the S parameters were measured by vector network analyzer from range of frequency 200 MHz to 50 GHz. Then, the computer was used to collect data and plot graphs using Python software after connecting to the vector network analyzer via a USB link. This is the practical configuration, the use setup for measuring the complex permittivity of liquids as shown in Figure 2, which was the use setup for measuring the complex permittivity of liquid. For the purpose of this demonstration, the coaxial probe is modeled as an infinite ground plane coaxial aperture, as shown in Figure 3a. In addition, the coaxial cable configuration and the equivalent circuit for the measurement system are shown in Figure 3b and the Figure 3c respectively. Figure 3c illustrates an equivalent circuit for the probe measurement. The capacitance CF represents the proportion of electric field located within the coaxial probe's own dielectric material. The capacitance C epsilon is from the surrounding field in the dielectric sample, and the loss in the dielectric enveloping the probe is represented by the conductivity G epsilon. Experimental validation. The results of the measurement of relative permittivity and the loss tangent in DPBS are shown in Figure 4a and b. In the frequency range of 200 MHz to 50 GHz, it should be pointed out that the value of epsilon r continues to decline over the test of frequency range starting from just under 80 and dropping about 12 to 50 GHz, while the loss tangent values start with approximately 1.5 at low frequency starting at 200 MHz and drops to 0.25 in the approximately 1 GHz range before increasing to over 1.5 at 50 GHz. Figure 5a measures value of relative permittivity at the loss tangent of the endothelial cell growth medium. As for the endothelial cell growth medium, it tends to have a similar relative permittivity and loss tangent to the DPBS with only a slight difference. During the test, the three liquids were measured and compared, and the results obtained from the measurements are shown in Figure 5a and b respectively. It can clearly be seen that the two liquids and DPBS and endothelial cell growth material are significantly different compared to the water in the sub-10 GHz frequency range, and after that, the epsilon r characteristics are more pronounced than similar across the measurement range. The loss tangent measurement results of the three liquids show that both DPBS and cell growth medium differ markedly from water in the range of the lowest frequencies. The default loss tangent of the DPBS and cell culture medium is approximately 1.5, while the default loss tangent of water is near zero. Following that, the loss tangents of the DPBS and cell culture medium continue to decline around 0.25 at 5 GHz. Then it increases to over 1.5 to 50 GHz, while the loss tangent of water is increased throughout the major frequency range. Also, they have similar characteristics to both liquids and the 10 GHz band and above. To sum up this study, the relative permittivity epsilon r and loss tangent of endothelial cells growth medium and DPBS have been investigated in the frequency range of 200 MHz to 50 GHz and compared with deionized water. In the frequency range of 200 MHz to 10 GHz, the epsilon r of water is slightly higher than the other two liquids, while it becomes a little less when the frequency is higher than 10 GHz. However, the loss tangents of water increases as the frequency increases, whereas the loss tangent of the cell culture medium and DPBS are 1.5 as extremely low frequency and decrease to 0.25 at approximately 1 GHz, before increasing to over 1.5 at 50 GHz. This is references, and thank you.
So we have time for some questions. Yeah, 5 to 6 minutes. So does anybody would like to ask some questions? No. No? Okay, then I have some questions. So is the presenter of the paper here? Please turn on your camera.
Oh, yes, I'm here.
Okay, so yeah, so your measurement has been performed using a standard measurement system from the manufacturer, right? So you use the system of Keysight technology, and it comes with the standard software. Is it the case?
Yes, sir.
Okay. You mentioned that you use Python in order to plot the graph. I'm not sure why you need the Python, because normally the system will give you the CSV file, and that can be plotted externally without using Python. I mean, use as a program to plot it, like MATLAB, Excel, whatsoever.
In this experiment, we use the Python to plot the data, which data were collected from the vector network analyzer.
But the program, the program will give you epsilon r and tangent delta automatically from the software that you have on your the notebook, which is connected to the vector network analyzer. Normally there is a software from the manufacturer, or you don't have that software and you have to calculate everything by yourself.
I do not have that software.
And you calculated everything by yourself using the...
No, I use the data from the vector network analyzer and transfer it through the computer notebook and use the program like Python and MATLAB to plot the graph and see the characteristics of them.
Yeah. What did the network analyzer give you as the data? Which data did the network analyzer give you?
The input reflection coefficient.
Okay, and from that, do you have to calculate something to get the epsilon r and the tangent delta? From the input reflection coefficient, did you take it and like transform or extract the epsilon r and tangent delta, or another program did it for you, or how did you do that?
The program did it for me because the loss tangent equal to epsilon double palm divided by the epsilon palm from the program, and we use the
So it's from the program from the manufacturer. So they have a program which extract this epsilon r and tangent delta for you, yeah?
Yes, sir.
Yeah, okay. So you can plot it using any software, MATLAB, Excel. So it did not have to be Python, right?
Yes.
Okay. All right. What is the goal of this experiment? Why do you want to have the DPBS to be? Do you want the DPBS to be similar to your medium, or is it by chance that they are very similar?
Because the results show the similar characteristics of them, but in this research, the goal we like to present the characteristic of the parameter of the growth medium used for human endothelial cell growth.
And the DPBS is used for what? I mean the medium is used for the cell growth, but the DPBS is for which purpose?
They are the same.
Oh, okay. But I mean DPBS and the medium is the same.
No. How can I say? We are going to use this characteristic to design by using the CST to create some kind of the sensor for to study the in the cardiovascular diseases, something like that, because in the recent years the measurements of the permittivity and diuretic properties at microfrequencies has been applied for untargeted characterization of biological fluids.
Okay, got it. So maybe we keep we can discuss at the university. I'm also from King Mongkut, North Bangkok. I think there are some special purposes of your research, but it is not very clear to me now, but okay, we can do it afterward. So anyway, thank you for the presenter, and we'll move to the next presentation. Okay, thank you. Okay, the next presentation is titled Dual Band Stop Filter for Chipless RFID Sensor in a Dielectric Constant Determination. So, and the presenter is Dr. Rathapong Suwalak.
Good afternoon, everyone. Today, I would like to present a dual band stop filter for chiplet RFID sensor in the dielectric constant determination. And my name is Rathapong Suwalak from Kingswood Institute of Technology, Ladakabang, Prince of Chumpon campus. ช่วง วง เจริญพานิช from Kingswood Institute of Technology ลาดกระบัง กิตติศักดิ์ แพรบัว ดนัย ต่อรุ่งเรือง ทิติพงษ์ เลิศ วิริยประภา เอกลักษณ์ กุล พลหา from Kingswood University North Bangkok. And the contents of this presentation consists of the introduction and the theory and design for the RFID sensor and also for the filter. And next, we talk about the results about the identification or ID and the sensing with the RFID sensor. And then conclusion and acknowledgement. For the printed microstep filter have been increasing in demand to integrate with the electronic board or for portable devices and also for the IVD technology. And in this figure, you can see on the left hand side is the couple line resonator, and the right hand side show you the step impedance resonator or SNR. And for this one, we use for the impedance matching. Okay. And also this one for the SIW or substrate integrated with guide. And this one also fabricate on the print circuit board or PCB. And this figure shows you the spiral and link resonator for use at the design to the wanted for operating frequency. And this is the stop load resonator, also design the stop for the wanted frequency or design frequency. Okay. And in this paper, the dual band stop filter based on the open circuit stop, and we also use the SIW transition for the transition the impedance between the tag antenna to the filter. Okay. And for this cable, we propose the both of the identification and the sensing of the dielectric constant of the material under test. And in this paper, we focus on the PCB board. Okay. Okay. For this one, we can design initial design for the band stop filter following to the question 1 and 2. And this paper, we use the FR4 substrate with the dielectric constant of 4.3 and the loss tangent of 0.005. The thickness of substrate is the 0.8 millimeter. Okay. And this is the structure of the filter in this paper. And you can see we use the stop, actually the open stop for the filter. And we use the SIW to transition the and between 50 ohm to 10. And this table shows you the parameter of the band stop filter. And you can see the length of the step 1 and 2 is equal to about 10 millimeter. And then we use that the filter to additional to the structure of IBD tag. Show you in this figure. And this is show you the chiplet IBD sensor system. We use the log periodic antenna for the leader, and we use the tag press on the PCB board to determine the dielectric constant of the materials. The distance between the reader antenna and the IVD tag about 20 centimeters. For in this paper, we call the chiplet IVD tag with band stop filter is the chiplet IVD sensor. Okay, and the direct constant of the material in this paper, we use the PCB board with the thickness of 1.6 millimeter. And the chiplet IVD sensor can be generated both the ID and sensing. For the ID or identification, we can get the IVD tag bit of 3, 0, 1, 1, 0, and 1, 1. And the 1 represent to the percent of the stop. The other one is the percent of the stop and assign at the 0. And this figure shows you the S parameter of the band stop filter. For this figure, the structure designed to the ID 10, and you can see the response of the S21 in the orange line. It can suppress the IF signal at the 2.2 gigahertz. And for this one, for the ID 01, and this one for designed for the frequency 2.7 gigahertz. And the last one is the ID 11. For this one is the we call the dual band stop filter at the 2.2 and 2.7. And for this one we use the 2 stop on the structure. And then we use that one for the IVD system, and we can get the magnitude of S1 show you the left hand side, and the right hand side show you the chiplet IVD signal. I mean the normalized signal and the sensor identification ID. So you can see the all of the direct constant and the tape can be separated by direct constant of 2.2, direct constant of 4.3 and 7.48, and all of this direct constant have the same identification at the 2.2 and 2.7. Okay, in the conclusion, the printed dual band and band stop filter is proposed that it add with the structure of the printed modified elliptical chiplet IVD tag with the perpendicular linear polarization to an IVD sensor. And this sensor is able to encode the unique identification or ID, and also for the IVD, also for the IF sensing in the radio frequency band of 2 to 2 gigahertz. And we propose the chiplet IVD sensor for identification to the 01, 10, and 11. And this paper focus on the PCB of the RT Duloy 40. RT Duloy 5880 and FR4 and LTCC. So for additional, the proposed chiplet IVD sensor with band stop can be generate more multiple ID with adding the more number of the stop. Okay, and the proposed chiplet IVD sensor can be candidate to the other materials. This research was funded by National Science Research and Innovation Fund and Kimmagut University of Technology, North Bangkok, with contract number FF 6526. Thank you for your kind attention.
Okay, we have 2 minutes for some questions. Anybody like to ask? Okay, okay. I have 2 questions. So, so the first question is, do you have to control the distance from the reader antennas to your sample? How far should it be?
In this paper, I fix the distance between the antenna of the reader to the material under test about 20 centimeter.
I see.
Because if we move far away, the transmission between the antenna and cactus, the loss is increased. Okay.
I see. Okay. Another question is that I saw 2 antenna on both ends of your sensor or tag, and one is the vertical polarized antenna, the one is horizontally polarized antenna. Why do they have different shapes?
Yeah, because we want to decrease the coupling between the receiving and transmitting antenna.
Okay, sure. Because they have several, they have different polarization.
Yes.
Different shapes.
Yes.
One of them looks like a monkey, and the other one is maybe just round. And any specific reason? Is that because of the bandwidth, or what is the reason?
Yeah, about the bandwidth of the operating frequency. As we try in this paper, we start at the 2 gigahertz to the 3 gigahertz. But if you that the microstrip antenna have the narrow band, so we have to modify the radiator like that.
Okay, thank you very much. It's time, for a good presentation. So it's time for the last presentation of this session. So let's thank the speaker again. The next presentation is titled Optimization of Interdigital Capacitive Sensor for Cell Culture Plates by Mr. Theppai Oo.
Good afternoon, everyone. I would like to present about the optimization of interdigital capacitive sensors for cell culture plates. This study was conducted by me, Theppai Oo, Dr. Wutam Jing Saksiri, Dr. Surami Chalang and Dr. Alongkong Pingping. For the layout of the presentation, I will go with the introduction, then I will go for the electromagnetic spectroscopy, electrode design, sensitivity, frequency response of the electrodes, and conclusions, step by step. So as an introduction, I would like to start with our goal for this study first. Our goal is to detect the abnormal cells, example cancer cells or cells which are infected by virus within the microfluidic channels. We intend to use the microwave technology to manipulate the cells and to design the electrodes to put under the cultural wells. Well, finally, to produce a first accurate and low-cost sensor. Traditionally, people have to rely on the optical detection system for the cell detection and sensing. And so they use stains or fluorescent dyes. In order to do so, the cell must be fixed and permeabilized. And it is a quite time-consuming task, and sometimes it causes a distraction to the cells and cannot be investigated for the further investigations. And it is costly and is not simple. For some scenario, example is a point of care. So people are seeking for the new technologies, and the new technology, which called the electromagnetic spectroscopy, has emerged. The advantage of the electromagnetic spectroscopy is it is low cost, non-invasive, contactless, non-destructive, and labor-free sensing. It even detect the cells in its living environment or in a cell culture environment. Different kinds of virus infection cells have different frequencies responses. There are basically three types of electromagnetic spectroscopy, which we call the electric cell substrate impedance sensing, ECIS, impedance flow cytometry, IFC, and electric impedance spectroscopy, EIS. For the electric cell substrate impedance sensing, it is usually depends on the single cell models. So when the cell's membrane blocks the current, when cells are adhered to the substrate electrodes, so that the cell adhere to the electrodes are considered as a capacitance. So in this kind of calculation, the one must consider electromedian interface, median, the electrode, and then the cell-to-cell junction. For the impedance flow cytometry, it's usually detected for a single cell, which pass through the flow systems. So the electrodes beside the fluid channels can detect the impedance changes signals. So a large part will occur when a DC signal is applied to the electrodes, which means that the reflection of the increasement of the resistance. For the electric impedance spectroscopy, it is widely used for electrochemical methods, and it uses low voltage frequency dependent AC signals to sweep the analyte. Usually is for the solution. So this kind of detection is usually used for the living cells that is always suspended in the solution. Example is the bacteria. So usually use this EIS is usually used for detection of metabolisms or proliferations of the cells. So there are some kinds of frequency influences over the impedance signals of a cells. So if we look at the frequency range between 10 kHz and 100 kHz, we can detect the signals of the size. And between the frequency range 100 kHz and 1 MHz, we can detect the membrane capacitance. And above 1 MHz, we can detect the cell cytoplasm and cellular levels. So based on the previous study, now we have designed our new electrodes, which will place under the cultural plate. So most of the sensing electrodes, they usually put the electrodes inside the cultural plate or inside the microfluidic channels, so that they are in direct contact with the cells. But for us, we put it under the cultural wells, so there is no direct contact between the cells and the electrodes. And we plan to use the low-cost vector nova analyzers as the measurement equipment. The electrical signal is capacitively coupled to the samples for this study without being in direct contact with it. In case of the spheroids, we use a 200 micrometer diameter polystyrene bead for this study. So the cross sections of the cultural well is also depicted in the figure 4. And the complete simulation model setup can be seen in the figure 3. So for the interdigital electrodes, we tend to use the fed with the SMA connector as a one-port connection. So the substrate here is we are using it as a phosphate substrate with relative permittivity of 4.4, which have the thickness of 1.6 millimeter, and the sensing area of 6.4 into 6.4 millimeter squares. So as you can see, based on the cultural plate, the sensing area is 6.4 into 6.4 millimeter, and this is fixed for all types of electrodes which we have designed. We have designed 5 different electrodes with different fingers and different widths. We kept the constant of the gap between fingers, GF 0.2 millimeter, the length of the finger 5.95 millimeter, and we're just changing the width of the fingers and then the numbers of fingers. So for the layout and equivalent circuits of the one-port interdigital capacitors, Ms. Schwebel have already simplified the equivalent circuits, which we can be seen in the figure 7. From that, we can extract the value of the admittance as per the following equation: 1 by Z0, 1 minus sensor reflection coefficient divided by 1 plus sensor reflection coefficient as sensitivity, as sensors. And from that admittance value, we can further extract the value of the conductance and then subtract that J omega C and see the value of the capacitance. So for the sensitivity case, we have tested in two conditions. One is the electrostatic and another one is the frequency response. So for this electrostatic, for this electrostatic simulations, for the sensitivity, we use the equation. Sensitivity is equal to C bit minus C no bit divided by C no bit into 100%. Here C bit means that when we put the polystyrene bit into the cultural well, and minus C no bit. Here C no bit means there is no polystyrene bit in the cultural well. So when we take a look into the table 2, it can be obviously seen that the numbers of fingers at 7, which I highlighted in the blue, have the most sensitivity, which is minus 0.96%, and which means that when we the negative value of the sensitivity means that when we put the bit into the cultural wells, the value of the capacitance decrease, as it can be seen by the third and the fourth column of the table 2. C no bit condition is always higher than that of the CB. So for the frequency response of the electrodes, we try to check their S11 values. So when we check the S11 value of our electrodes, it can be seen clearly that all the S11 values is ranged between minus 0.0035 to minus 0.0005 to minus 0.00035 between the frequency range of 0 to 10 megahertz. So it can be clearly seen that since the value of the S11 is almost 0 or near 0, all the power which fed through by SMA connector is reflected from the sensor, which means that all the powers are not being absorbed by the sensors. So if we take a look at the S11 clearly, then we can see that 3-finger design and 5-finger design, 7-finger design, 9-finger designs, and 11-finger designs. And the S11 response of the 3-finger design still still close to the 0. So, but there's no clear relationship between the number of fingers and S11, and we further need to analyze for that. So when we look into the comparison between the simulated S11 of the electrodes with or without polystyrene bit, here in the solid lines represents the electrode with beads, and the dotted line represents the electrode without the bead. So in case of the 3 fingers, which I have highlighted here as a blue color, we can see that the best sensitivity in case of 3 fingers, not as 7 as an electrostatic case. So this thing is for the frequency response of the electrodes, and we will go further detail for this as well. So by looking at all of the things that we can see the most sensitivity and the most changes is that in the case of scenario of the 3 fingers design. So we minus the S11 difference, S11 value between with and without the bit in order to know which one has the most sensitive part of the sensing part is the 3-finger design, as I highlighted here in the 3-finger design. And when we take a look into their difference, it can be seen that 3-finger design have the higher value than that of the others. So in case of the frequency response, 3 fingers still the best, but in the electrostatic case, 7-finger is the best. So these two will have to be find out the reasons and finalize for the future study as well. So when we take a look into the difference between the conductance value, here in the solid line, which means that there are 3 fingers electrode with bead, and the dotted line means that the 3 fingers electrode without bead. We choose the scenario of the 3 fingers because it shows us the best sensitivity for this. So when we take a look into the difference between these two, we can see that the conductance over frequency of 3 fingers sensing difference is increasing with the increasing frequency. So the same thing goes for the susceptance value. The difference between the electrodes and the bead and without bead increase with the increasing frequency. So for the conclusion, we have studied that the electromagnetic spectroscopy is proposed for stress sensing in the cultural wells, and we use a 1-port interdigital electrode in different geometry. We simulate both in electrostatic and high frequency regimes, and the specific number of fingers can provide the largest sensitivity regardless of the number of fingers. The difference in S11 and conductance value increase with the increased frequency. So for the future study, we will fabricate those electrodes and measure with the simulated results. Thank you very much for your attention, and any questions are welcome. Thank you very much.
Thank you, Pai. This is actually my own paper, so I cannot ask myself anymore. I asked Pai everything I would like to ask already. So if somebody else would like to ask something about this work, you have the opportunity now, please. Any question? Yeah, doesn't seem so. Okay. Therefore, before we close the session officially, I would like to ask all the participants here to turn on your camera so that we can take a virtual group photo. So if you are comfortable with that, please. So seems to be all of us here. Okay, we take the screenshot. 1, 2, 3. One more time. Okay. Okay, thank you very much. And I would like to close this session, and many thanks to all the presenters and participants of this session. Okay, see you around then. Thank you and bye-bye. Have a nice day. สวัสดีครับ